Before we begin officially, just some introductory things. This is Physics 9B. Hopefully you are all here for this class. We're going to be talking about wave mechanics, sound, light, and thermodynamics. The lectures, and you guys are all here, so you probably know this, but the lectures are Monday, Wednesday, Friday from 10 to 11:40 a.m. My office hours have been set. The TA's office hours have also been set, but I don't know if they've set them up on Zoom yet. My office hours are going to be on Tuesdays from 11 to noon. There's going to be assignments. There's going to be quizzes every lecture besides today. There's going to be homework assignments, labs, discussions, and so on. So go check out the syllabus. The quiz that's on the quiz that's tomorrow is going to be mostly on the syllabus. Like there will be syllabus questions regarding academic honesty, things like that. So make sure you read over the syllabus. You read over the pages on Canvas. There's pages on, yeah, sorry, the quiz on Wednesday. You're right. If you go to the pages tab on Canvas, you can click view all pages, and then there's a bunch of informative pages there. There's a page on how to use Gradescope, a page on the exam policies, a page on homework policies, a page on Siteboard, and so on. So you're going to want to look at those too, because that kind of material will also be on the quiz. So take a look at that. I want to make sure everybody's familiar with how this class is scheduled, because it is, it is online. It is still relatively strange. So take a look at that and we'll go over it. Just so you know, my email is shblitz@ucdavis.edu. You can email me with questions, but like the syllabus says, I really prefer not to get like physics questions via email. Yeah, it'll be basically identical to 9A, except we have quizzes more frequently. I prefer not to get physics questions over email. And in fact, I prefer to get no questions over email because they're a pain to keep track of. Instead, use the Discord server. You can ask me questions and I'll respond a lot faster. Like if you have some bureaucratic question or some administrative question, fine, shoot me an email so we have records. But it's definitely like the easiest way to reach me will be on Discord. And there's a whole Discord server for asking questions about physics. And so you can like ask each other questions and help each other out. So I would recommend 100% you look into Discord. If you're not familiar with what it is, Google it. You guys are clever people. It's basically a chat room that we can use for relatively official purposes for this course. I suggest everybody sign up. There's a link at the bottom of the syllabus. I also made an announcement about it yesterday or 2 days ago, maybe 3 days ago. Anyway, take a look. Right now, there's only 45-ish people enrolled or in this course on the course Discord. If we get that number up to 80, 85, we'll hit that critical mass so that questions are getting answered like that. So everybody sign up, everybody use it. It'll be a great help for your summer session because I know summer sessions can be tricky. Right, so let's jump in to course material. So we have a lot to go over today. I hope we'll make it. Oh, one more thing. The approximate course schedule is just that. It's an approximate schedule. Since I last taught this class about a year ago, the curriculum has changed relatively significantly. So the amount of material that I can cover in each class, I'm just not aware of. So if we don't make it as far as we would like, that's fine. I'll just change what material we cover for the homeworks, what material we cover for the exams, and so on. So it is just an approximation. I'm going to try to stick with it, but it might be too fast. Anyway, with all of that out of the way, we have about 97 minutes of lecture. So I'm going to take a sip of water, and then, no, the quizzes will be right before lecture. Quizzes are from 9:55 to 10:05. Every lecture. And if you are still struggling with Discord, if you click on announcements, then there will be a place where you can, no, if you go to welcome, you will have to accept some rules. Once you click the check mark by reacting, you will get access to the course selection channel, and then you can use that to select this course. You only need a webcam for the midterm, so get one in a few weeks. Go to Walmart, pick one up for $10. They're relatively easy to find. Anyway, let's jump in with course material. So like I mentioned, we're going to be talking about waves first. That's the very first thing we're going to cover. So let's answer the question, what is a wave? By the way, it's nice to see some familiar faces here. So a wave, and this is like a formal definition, is a disturbance that propagates through points in space at a constant speed. And I'm going to try my best to write neat, but I also have to write fast, so sorry about that if it looks bad. If you can't read something, let me know. So we can give some examples of this. By the way, I'm more than happy to answer questions in chat during lecture. However, I will typically only answer questions like about the actual lecture material. If you have questions about administrative things, bureaucratic things, or about homework or whatever, we can talk about those after lecture. And I will always stick around for 10, 20, 30 minutes after lecture to answer any questions you have. Right. So let's talk about examples. So you guys all know examples of waves. Like there's a common one, ocean waves. Those things that show up on the beach, those are waves. Other waves that you may be more familiar with, or that you may be less familiar with rather, sound. You've probably heard the phrase sound waves. Sound is another type of wave. Finally, one that's perhaps the most surprising, light. Light waves, you've probably heard that too. In fact, there's another one which is even more surprising and was only discovered or only experimentally verified like 4 or 5 years ago. Gravity. Gravity propagates in waves, turns out. We discovered this like 4 or 5 years ago at the, what's it called? Oh, I should know this. I was at the event. Oh, what was it? Okay, I can't remember what it's called. LIGO, yeah, LIGO, thank you. Long Distance Interferometry Gravitational Observatory, I think is what it stands for. I know LISA is the one that they're building in space. Anyway, big deal. Gravity also propagates in waves. So, but this isn't enough. This is like a qualitative description of what a wave is. This is a physics class, a calc-based physics class. So we have to describe things mathematically. So how do we do that? Well, we do that with a wave function. So f of x, which is our wave function, would measure how big the disturbance is at position x. So you would plug in a position and f of x would spit out how big the disturbance is. If it's an ocean wave, it might spit out the height. If it's a sound wave, it might spit out like the pressure. If it's a light wave, it might spit out the amount of photons or something like that. But it has to be more than this, right? Because waves also travel in time, right? Like the height of an ocean wave at a given place changes with time. So we need to account for that too. So to account for that, all we do is we just make our formula a little bit more complicated. So what we're going to do is we're going to basically just make our wave function depend on both position and time. So we would just write f of x and t. Now for what we're about to do, we're going to assume that we're talking about one-dimensional waves, and we'll talk about multiple two-dimensional waves, three-dimensional waves in a little bit. But for a one-dimensional wave, just think like a wave that's just going down a string. You like flick a string up and then it goes down. For a one-dimensional wave, what we can do is we can think about what happens just from observing it. So every t seconds, the wave moves. The wave moves vt units in the x direction. This is, I mean, like waves can move in directions besides the x direction, but this is just an example. So this would be like if x is the direction of the string, you flick the string, the wave travels that way, right? You just get a little bump that moves down. So this v here tells us how quickly the wave propagates. It's the speed of propagation, or the wave speed is often what it will be called. And so if this is how a wave moves, if it just takes the same shape and then just moves it a little bit every unit of time, then we can actually describe the wave function f of x and t in terms of a more quantitatively descriptive way. If this is the case, f of x and t is equal to, in fact, it's just a function of x minus, and I'm going to write minus plus vt. So what this is saying is that the wave has shape, say, f of x. You could just draw the shape of the wave. Maybe it looks like a bump, right? This would be f, this would be x. But the place where that x is evaluated is shifted by an amount corresponding to the shift or to the time duration. Oh, it's a minus plus, and I'll explain this in a minute. So this shifts linearly in time. it's like plus or minus, but just in the opposite order. And the reason I did that is because if we have a minus sign, this means that the wave moves to the right, which is the plus x direction. And if we have a plus sign in the middle, we have that the wave moves to the left. I could have done plus or minus. The only reason I did minus plus is because people kind of intuitively assume, or it's not intuitive, it's a convention. Imagine the positive x direction to be associated with, or to be the right. And so that's why we want to use minus plus. So if you have a minus sign, then it moves right. If you have a plus sign, it moves left. And the reason why it moves right, by the way, should be fairly clear from like your pre-calc class. If you shift a function, if you have x squared and then you make it x minus 5 squared, it shifts the whole parabola 5 units to the right. And that's because you're decreasing the argument. So everything that was 5 units to the right is now what it would have been 5 units to the left. You guys can play around with this on your calculator to try to intuit what's going on. But we can just give some examples. Oops. Come on, scroll, please. By the way, occasionally my tablet will have technical issues because this tablet's like almost 7 years old now, or 6 years old maybe. So you'll have to bear with me. Sorry if that happens. So one example would be like sine of x minus 3t, right? So in this case, v is 3, x is x, t is t, and f of x is just sine of x. Another example might be g of x and t. We don't always use f, by the way. Maybe this is x plus 5t. This is also a perfect example. In this case, g of x would just be x. And then if you plug in, so g of x would just be x, and then you plug in x plus 5t for that variable. Another example might be h of x and t might be the exponential function, that's e to the something, of minus x plus 19t squared. That would also be a totally valid example. Basically, any time that you have x plus or x minus plus a number times t, that would be an example of a wave. Now, it's not always clear right from the get-go that something has this property, that it has that you can write it as a function of x minus plus vt. Sometimes it's been factored or rearranged or whatever, so it's a little bit harder to see. So depending on how good your algebra is, sometimes you can just rearrange it so that it appears in this form. But it's not always that easy. So there's another way that we can tell if a wave function of x and t describes a wave. That is, if it doesn't have this form, we can still check if it describes a wave. And the way that we tell is we just plug in our candidate wave, our thing that we're trying to check, into something that's called the wave equation. So the wave equation is a partial differential equation. You guys have all taken 21C. You should all know about partial derivatives, I believe, and you're taking 21D now, so I don't actually know what 21D is about. But anyway, so the wave equation is an equation that tells us, or is an equation that all waves have to satisfy. So in particular, if f of x and t is a wave with speed v, then we know there's just automatically, then automatically that wave has to satisfy a certain equation. And that equation is d squared f dx squared equals 1 over v squared d squared f of x and t dt squared. Have you guys all seen partial differential or partial derivatives? Is that a thing that you guys have seen already? I mean, you should have seen it in 9A. Like, it's certainly a thing in 9A, but I thought that was something that was covered in 21C, maybe not. Okay, so at least it seems that everybody has seen it, so that's good. So this is just saying, if f is a wave and it travels at some speed v, then this equation is true. And so what you can do is you can take some candidate wave, you can plug it into the wave equation and see if something like this pops out. Maybe you don't know what the speed is, but so long as you just get a number in that spot where v is, if it's like 18 or 25 or whatever, then that means that it satisfies the wave equation for some particular speed. And you can figure out what that speed is based off of what that number is. But if instead you end up with like v squared plus x squared or something down here, then it doesn't satisfy the wave equation and your candidate wave isn't a wave. So we can actually take this equation apart from a physics perspective, which we can do. And it's actually kind of arcane. So what it means is, remember that the first derivative of a function is its slope. The second derivative is its concavity, its convexity. So what this wave equation is telling us is that the convexity, or the concavity of a function, or of the wave rather, and by the way, like when I say the convexity or concavity of the wave, I really mean like, is it like concave up? Is it concave down? How concave is it? Like we're literally talking about plotting it on a graph. The convexity or concavity of the wave, which is measured by the second partial derivative with respect to x, is proportional to the acceleration of the wave, or to the acceleration of the disturbance rather. And the proportionality constant is just 1 over v squared. And acceleration is just this 2 time derivatives of some displacement, right? And that's all this term is. So all we're saying is that the convexity of our disturbance is proportional to the acceleration of that disturbance. That's it. That's all we're saying. And so on the homework assignment, the first homework assignment that will be put out on Wednesday, I'm actually going to ask you to check that for some generic function, f of x minus plus vt, that it satisfies this wave equation. And you'll have to flex your calculus chops, but you guys have all taken 21A through C, so you should be fine. So the story changes in 2 or 3D. So we're just going to talk about 2D for now, but 3D generalizes pretty easily. So imagine for a moment that you throw a pebble into a lake, right? If you throw a pebble into the lake, there's going to be ripples going out. Those ripples are a wave, right? Like it's a disturbance in like the surface of the water. So it's like a little ocean wave, and it's traveling at a fixed speed. The circles move outward at a fixed rate. So we've already established that in one dimension, this is like just in the x direction, or just in the x direction would be an example. Like a string, like a guitar string would be an example of a 1D wave. In one dimension, the wave function has to satisfy or it has to be of the form f of x minus plus vt. And by the way, it's not like both minus and plus, it's just one or the other. In this case, if a wave was traveling to the right, then it would be a minus sign. So I'm actually going to choose minus where plus x is the direction of travel. So you can imagine doing the same sort of treatment for a wave, for like the ripples on a pond, right, or in a lake. If we instead use, so what direction is the wave traveling for the ripples in the lake? Well, it's not traveling in the x direction because it's also traveling up and is traveling to the side. So viewed from above, you can imagine that it's traveling radially outwards, like it's going out, right? And so we might just use the polar coordinate r. So for a radially outward wave, we might guess that f of r and t, where r is the radial coordinate, it's in polar coordinates, should be equal to f of r minus vt. That's a totally reasonable thing to guess, where r in this case points radially outward. Now, that's one way that we could try to generalize this notion of waves to 2 and 3 dimensions. However, radial waves aren't the only type of waves, so we should be able to characterize this in terms of Cartesian coordinates. Think, for example, they're called plane waves. Think like, I'm trying to come up with a good example that you guys would be familiar with. Okay, I can't actually think of any. But I mean, the coordinate that we gave for our wave equation in one dimension was in Cartesian coordinates. So we should be able to give a similar equation in Cartesian coordinates in 2 or 3 dimensions, right? We should be able to generalize that. So let's do that. Alternatively, we can use Cartesian coordinates to generalize our wave equation. And we just add more terms. And so then there's a reason that we're using partial derivatives. I mean, we had to in the first case anyway. There was x and t. So we might write in 2 dimensions d squared f dx squared plus d squared f dy squared. Maybe that should be equal to 1 over v squared d squared f dt squared, right? Put x and y on the same footing. Yeah, ocean waves are, I mean, that's a good example. If you assume the shore is infinitely long, then yeah, that would be a good example because the waves kind of come in like this. They come in like as lines kind of going this way. And sure, yeah, maybe that's a good example. This is like viewed from above. Yeah, and so doing this in Cartesian coordinates does make sense. I mean, there are other types of waves that would be examples of plane waves that kind of just travel in lines and they just go towards the thing that we're interested in. And they don't have like a circular shape, they have like a planar shape. Anyway, so this would be a reasonable extension to do. We're treating x and y on the same footing because there's no reason they should be treated any differently. And so this might be our 2D Cartesian coordinate wave equation. So then the question is well, it doesn't matter what coordinate you choose. It doesn't matter what coordinate you choose, what coordinate system, like you're just describing a physical thing. Nature, the universe, doesn't know about coordinate systems. The universe just does things. And so regardless of the coordinate system that you choose to use, you should be able to describe the same thing. It just might be more messy mathematically in one coordinate system than another. So these two equations, if they're both correct, if they both describe waves, should be compatible with each other. You should be able to plug one into the other and get that, for example, by plugging in the wave function f of r and t into this Cartesian wave equation, you should get that it satisfies that equation. So we're going to check that. And this is pretty math heavy, so you'll have to bear with me. I'm going to probably go by it pretty quick. This is done in detail in the LibreText textbook. It's also done in detail in my lecture notes. So do check those out. But what we're going to do is we're going to try plugging in f of r and t, or f of r minus vt, into the above equation. And so we're going to have to use our Cartesian, or our knowledge of polar coordinates and Cartesian coordinates, to rewrite one in terms of the other, and then we can do our math. And so the goal is if the left hand, if we find the sum of the second partial derivatives in the spatial directions, and they happen to be equal to, up to a constant of proportionality, the second partial derivative of the temporal direction, time, then that means that they do satisfy the wave equation. And that means that they are consistent. But on the other hand, if there's just no one constant v that makes this statement true, then that means that they cannot be compatible. The lecture notes will be posted every lecture, or after every lecture. So let's check this. So we have some calculus to do. And I'm probably going to skip some steps, but they're not going to be hard steps. So polar coordinates, in polar coordinates, the radial distance r is equal to the square root of x squared plus y squared. It's just the standard Pythagorean theorem. And so we can actually use partial derivatives to find the change in r with respect to x. This would just be x divided by r. It's actually x over square root x squared plus y squared, but square root x squared plus y squared is x anyway. And similarly, the derivative of r with respect to y is y over r. Okay, this is just some relatively straightforward calculus, just taking derivatives. And so, in fact, I'm going to do one more simplification procedure. I'm going to let g of r and t, this is just some random function, some simplifying thing. I'm going to let this be equal to r minus vt. So with that in mind, the derivative of g with respect to r is 1, and the derivative of g with respect to t is minus v. We're going to need that. So if we know how g changes when r changes and g changes when t changes, how does g change when x changes? So we can use the chain rule for that. The partial derivative of g with respect to x is just the partial derivative of g with respect to r times the partial derivative of r with respect to x. Technically, we would also need a second term, partial derivative of g with respect to t, partial x, but partial t, partial x is 0, so we can drop that term. Partial g with respect to r is 1, so this is just x over r. And similarly, the same thing is true with partial g with respect to y, that's just y over r. Okay, this is all set up, and the reason why is because this is going to get messy with all these coordinate changes. Okay, now we need to figure out how does, so what we want to do is we want to take two partial derivatives of f in each of the three possible ways, x, y, or t, right? And then we want to check that these things are equal on the left and right hand, the left and right hand side. So let's do that. So partial f with respect to x, we're going to use the chain rule. This is partial f partial g, because f can be written as g of r and t, right? Because g is r minus vt, times partial g partial x plus, no plus, that's it. And we already know what partial g partial x is. So this is just partial f partial g times 1, no, not times 1, times x over r. Okay, and then similarly, partial f partial y, which we also need, is partial f partial g times y over r. I know this is going pretty quick. We're going to get to a punchline soon, though. So now we just have to do another derivative of each of these in the x direction. That'll involve a product rule and a chain rule again. So this tells us that the second partial derivative of f with respect to x is the partial derivative with respect to x of partial f partial g times x over r. We're going to have to hit the df, or the partial f partial g with the d by dx. We're going to have to hit the x with d by dx. We're going to have to hit the 1 over r with d by dx. So this is partial squared f partial x squared, or sorry, partial g squared, times dg dx times x over r. So this is the derivative hitting the first term. We're doing the product rule right now. Second term in the product is partial f partial g. And now we have to hit the second term. Well, we know what partial x is. That's just 1. So it's just 1 over r is the first term. And then we have to do partial g, or we have to take the derivative of 1 over r. So this is 1 over r squared times partial r partial x. All right, which we can rewrite combining all of these terms. We get that this is, and again, I know this is a lot, but I promise we're headed somewhere. This is partial f partial g squared times x squared over r squared. So we just have 2 x squared over r's from, or 2 x over r's from dg dx, plus partial f partial g times 1 over r times 1 minus x over r squared. All right. Again, it's just calculus. And then we can do the exact same thing for two derivatives of f with respect to y. So I'll just write that out just so we have it for access later. This is partial f partial g squared y squared over r squared plus partial f partial g 1 over r 1 minus y over r squared. Okay, those are the results that we need. Now we just have to do this one more time for time derivative, but the time derivative is easy. And that's just because partial g partial t This guy is just minus v. And so we don't have, like, it's not a function of t again. So it's just going to give us constants. So partial f partial t is just partial f partial g times partial g partial t, which is minus v times dfg dg. And so two derivatives is just, well, v is just a constant, so we don't have to worry about that. We just do it one more time and we get another factor of minus v. So we have d squared f dt squared is v squared times partial f squared partial g squared. Okay, that's all the setup. Now, so I'm going to put boxes around these just so you can see what the results that we have. Now we're going to slap all these together. And so, well, let's slap the first two together because we want to take the sum. So partial f partial x squared plus partial f partial y squared, well, that's just equal to, we can just do some factorization. It's partial f partial g squared times x squared plus y squared over r squared plus partial f partial g times 1 over r times 2 minus x plus y over r. Okay, just doing algebra. And then simplifying again, noting that x squared plus y squared is r squared. This is just d squared f dg squared plus df dg 1 over r 2 minus x plus y over r. And the important part is that this left-hand side of what would be our wave equation has two terms. And namely, it has a term that looks like this. Whereas the right-hand side of what would be our wave equation, yes, sorry, that should be r squared. What would be our right-hand side of the wave equation only has one term. So there's no possible way that they could be equal. So that means that they're not consistent. The wave equation that we gave cannot possibly describe something that propagates or whose disturbance propagates according to this wave function. Just impossible. They just are not compatible. So one of them has to be wrong because you can't have inconsistencies in nature. The question is which one do two-dimensional waves actually obey? Do they propagate just as linear shifts in time, or do they propagate obeying some differential equation? So, okay, yeah, I can explain why they're different. So we found that the left-hand side should look like this, whereas the right-hand side would look like this with a 1 over v squared. Basically, the left-hand side has two terms. It has this term that's two partial derivatives, which matches the first term in the time on the right-hand side. But then there's the second term on the left-hand side, which doesn't match anything. So it cannot be the case that the left-hand side is equal to the right-hand side. Those two things just aren't equal. There's no possible choice of v that you can choose here that will make the left-hand side equal the right-hand side. It just doesn't work. Hopefully that's relatively clear. But if not, do stick around afterwards and we can talk about it again. So it turns out that, and we will go over this again in the, or hopefully later today if we make it that far, but it turns out that our guess for the wave equation was correct, i.e. the Cartesian version of the wave equation does describe real world waves, and you would have to go and figure that out by like doing measurements. And that our initial guess for the wave function that describes two-dimensional waves just wasn't right. Two-dimensional waves don't have that property that they propagate that way. And perhaps you can see why. Waves are just a property of nature. So like most ideal systems, they will conserve energy. And so if you think about it, if you like drop a pebble and the waves are just as high really close to where the pebble is as they are far away, then you'd have like a lot more energy. You'd have the energy increasing as you get further away because the height stays the same, but you have like more wave. And so that's how we're going to explain it. But the bottom line is that in this case, the waveform should change shape. It changes shape with distance rather than just having the same shape at any position. So the waveform might look something like this. You have F here, you have R here, and then you drop your pebble in and it looks something like this. And it, the ripples get smaller as they get further away. And the reason this is incompatible with our guess is that our guess says that if you move outward in position, if you go from say R equals 1 to R equals 2, you can get back to the same height by just moving forward in time, which would just say that the height at one point in time at a place further to the inside is going to match the height at a corresponding later point in time further to the outside. But that's just not what happens. The height actually decreases as they go further out. And so they can't match each other. Like it's the wave function that we guessed implies the shape always stays the same as the wave travels. But as we just determined, the shape of a wave, of a two-dimensional wave, like a ripple in a pond, the height gets smaller as it gets further away. So just as a quick aside, and maybe you guys have seen this notation before, but this is just a notational thing. So in general coordinate systems, so Cartesian coordinates or polar coordinates or ellipsoidal coordinates or whatever, in 2 or 3 dimensions, we can write the wave equation in a simpler way, or in a more compact way. And that's using the double gradient or the Laplacian symbol. Yeah, no. So the lecture notes are going to be posted after lecture, certainly. But I can scroll up just a little bit. So the symbol that we're going to use here is that one. It's an upside down triangle with a squared symbol. And this would be on F equals 1 over V squared partial F partial T squared. And so this symbol, this just means the sum of spatial double derivatives. Spatial. And this is a coordinate-free expression, so that's why it's sometimes used. So you could write this in Cartesian coordinates, or you could write the same expression in polar coordinates, and it would look different. It wouldn't look the same as the Cartesian coordinates, but it would represent the same thing physically. Right. So I won't really use that notation very much because it can be confusing for you guys. However, if you do see it, that's what it means. All right. So let's step away for a little bit from 2 and 3 dimensional waves. Oh, by the way, I didn't mention this, but in 3D, this wave equation generalizes exactly as you think it would. You would just add another term on the left-hand side, which would be partial F partial Z squared. And that would be the 3D wave equation. And it also happens to be the case that 3-dimensional waves, these are things like sound waves, also obey that 3-dimensional wave equation and don't obey that a guess that looks like that. So that's an aside. But let's retreat back to 1D for a little bit, just for a moment, because we can talk about some more properties of waves in a more general way if we restrict our focus. So let's talk about properties of waves, or let's talk about the periodicity of waves, rather. Periodicity. So not all waves have to do this, but some waves can repeat themselves. And waves that do repeat themselves are called periodic waves. By the way, you might be thinking, well, don't all waves repeat themselves? And I mean, the answer is clearly no, right? Like if I clap my hands, that's one wave. That's just a wave pulse that just goes out into the universe and it never repeats, right? So it doesn't have to repeat itself. So the question is how can you tell, just like mathematically, how can you tell if a wave is repeating itself? Well, if you're given a wave function, say f of x and t, what you can do is you can plot a snapshot of that wave. So what you would do is you would plot f of x and t at some fixed time capital T, and then you plot it with respect to x. And if you see, when you plot this, say on your calculator, or you do it by hand or whatever, if you see something that looks like it's repeating itself, then you might have a periodic wave. So this might be called what's called the snapshot method. you take a snapshot of the wave, and it's called a snapshot because it's like you take a picture of it, and then you just then you look at that single standing picture, and if the positional distribution of the disturbance repeats itself, then likely the wave itself is periodic. Similarly, you can also just like get a camera and then just zoom in on a single part of the string or a single part of the wave and see what it's doing over time. You can also, this might be called the fixed position method of measuring or of testing if a wave is periodic or not. And so here you just plot the disturbance against time. So you pick some fixed place, say x equals a, and then measure the disturbance with time. And maybe that looks something like this. But if that repeats itself, that would also be another indicator that this is a periodic wave. And waves repeat themselves at times and not repeat at another time in a different location. Yeah. So periodic actually, so from a completely rigorous perspective, periodic means that it repeats itself for all time and all space. Most real world waves don't do this, right? In fact, really all real world waves don't do this. But to a certain extent, we can approximate some waves as having this property, which is useful. So we can actually describe this property mathematically. If we're given a wave function, say f of x minus plus vt, that the fact that it's periodic means it has to be the same at some later time or at some later place. And we can do that by just adding a number. So we would describe that as saying that f of x minus plus vt should be equal to f of x minus plus vt plus n times, say, a number delta. That's the Greek letter delta. It looks like that. It's like a D, but like curlified, I guess. I don't know. It makes the D sound in Greek. And the point is that this is just some fixed constant. So, and n, by the way, here, n is just an integer. So it's any integer, -1, -2, 0, 1, 2. So the point is if it's true that for some delta, this equation is true for every single possible integer, then your wave is periodic. And the reason why this makes sense is because imagine for a moment that you're looking at the snapshot method. Pick an instant in time, say t equals 0. This would mean that f of x, because t is 0, should be equal to f of, say, x plus n delta, which means that the disturbance is at the same height at different places, periodically spread out through space. Similarly, you can do the same thing with the fixed position method. Set x equal to 0, and then ask at different instants in time, this would be requiring that those instants in time have the same level of disturbance at different instants in time, right? So this is a good way of testing for periodicity. In fact, this is the definition of periodic. Now, periodic waves have special properties. And this is why we like periodic waves so much, because we can describe them very, very specifically. So one property that a periodic wave has is something called a wavelength. The wavelength is given the Greek letter lambda. I don't know what it looks like. It's just that. You'll have to get used to writing Greek. You learn Greek as a physics. When you learn physics, you learn Greek. Sorry. So the wavelength is the distance between repeated patterns. So if you take a snapshot and then you measure the distance between two repeated patterns, that is the wavelength. Then there's the period, which is where periodic comes from, which is given the Latin letter capital T. This is the amount of time between repeated patterns. So this is, if you use the fixed position method, this would be how long does it take to get back to where it started. There's also another useful property called frequency. Frequency is related to the period. It's just how many times per second. By the way, this is using the Latin letter f. That frequency is a number that tells us how many times per second does it repeat. So maybe if it oscillates 3 times per second, like if you look at a fixed instance, And you see that it goes up, then down, then up, then down, then up, then down. 3 times in 1 second, the frequency would be 3 per second, or 3 hertz. Hertz is the unit for frequency. And so all of these properties, as well as the wave speed, and by the way, wave speed also makes sense for a periodic wave because you can look at a certain disturbance and you'll see that it moves. And it moves in precisely the distance that the period would require for that place to move up again. These properties can all be related to one another. So algebraically, or not algebraically, so we can just think about how these might be related. So the wave repeats itself after t units of time a distance lambda away. Yeah, it's hertz. Hertz, which is abbreviated Hz. That's 1 per second, 1 cycle per second. So if you look at a snapshot, it's going to move lambda distance in 1 period. And the reason it does that is because in order for that peak to get to the other place, in order for, let me draw a picture really quick. Right, so this peak, we know that over 1 period, this peak will go down and then back up, right? That's 1 period. But also the wave is traveling, it's a disturbance that propagates. So that means that this peak must replace that other peak in that same amount of time. It has to travel 1 wavelength in 1 period. And so that means that the wave travels, this tells us how fast the wave travels. It travels at speed v equals lambda over t. So this is just one of the most fundamental relationships about waves. It tells us how the wavelength relates to the period of oscillation, and those two things combined give us the wave speed. Similarly, a single cycle, this is 1 oscillation, takes 1 period to occur. So we can relate the frequency to the period. It tells us that f, the frequency, is 1 divided by the period. So if it's oscillating 2 times, if it takes 2 seconds for it to repeat itself, then it's undergoing 0.5 cycles per second. And so we can use that relationship to plug that in for a speed. So this implies, and this is a more frequent way of writing the speed, that the speed is lambda times f. It's wavelength times frequency. So by the way, this is only true for periodic waves. Wavelength doesn't make sense for non-periodic waves. Now, by the way, I do this thing in my lectures where I will link to example problems from an external textbook, which is mentioned in the syllabus. So this is the first point in this lecture where there would be an example problem that you can use. So I would suggest that after lecture, you go take a look at the lecture notes that I'm going to post. There's a link there, and you can take a look at the problem. I suggest you do these on top of the homework. They're good practice, and they're good for solidifying understanding. Another property of waves is called polarization. And this one's a little bit harder to explain. So waves aren't always, I should actually write this. Waves aren't always displacement waves. Now, a displacement wave is like a wave on a string. It's like a physical object is displaced, it's moved in some direction. Usually, or actually always, that displacement has to be perpendicular to the direction that the wave travels. So, right, so if I flick a string, the wave goes that way, but the displacement is up and down, right? So like the one piece of string moves up, it pulls another piece of string with it, and then it goes down, and then it goes across. The wave moves this way, the displacement is this way, but in particular, or the disturbance is vertical. But in particular, that disturbance takes the form of a physical object being displaced a physical distance. But not all waves are like that. This is just the easiest one to demonstrate. But the important part is that they do always have a direction. And it's not just the direction that the wave propagates in. They also have a disturbance direction. Like, for example, what direction does a sound wave, or what direction is the disturbance of a sound wave? Well, a sound wave, if I like echo, and the sound wave goes that way, do the air molecules move up and down? Do they move left and right? How do they move? Well, it turns out the air molecules will move left and right. But even if we're not talking about displacement, if we're talking about pressure, we can talk about the direction in which the pressure is changing. And so the direction of the disturbance, not the direction in which the disturbance moved, but the actual physical direction in which the quantity we're measuring changes in, that is called polarization. So let me show you a link really quick that describes this picture relatively well. This would be an example of a longitudinal polarization. So here we have hopefully you guys can see all of this. Here we have two examples. We have transverse waves. These are the kind of waves that we've seen in strings. See how each individual like little dot is only moving up and down, but the whole thing, the whole wave is moving from left to right. But the individual particles are moving up and down. So in that sense, this is a transverse wave. Transverse meaning that the wave's polarization, the direction of the disturbance, is perpendicular to the direction of motion. The other type, which is a little bit harder to grasp, are longitudinal waves. So these would be waves where the whole wave moves in one direction, but also the disturbance is in that same direction. So look at like a given fixed particle here. So if we this would be an example of like a sound wave. So if you look at this little red dot, actually you can just look at this bottom diagram. If you look at this little red dot, these dots are moving left and right. Those are like air molecules moving left and right, just as, and it's not traveling with the wave, it's just moving left and right, just as the wave also moves to the left. So longitudinal means that the wave polarization, which is the thing that tells us which direction a particle in a wave would move if it were a displacement wave, that polarization, if it's in the same direction that the wave travels in, then it's called longitudinal. If, on the other hand, it's perpendicular to the direction that the wave travels in, like in this transverse wave case, it's called transverse. This link, by the way, if you want to read about it, this link is also linked will be linked in the lecture notes, so you can go take a look at it then. Now, there's more to be said here. In particular, the particles don't actually move with the wave fronts, which is kind of bizarre, and we will talk about that when we talk about sound. And so this is just to get at the fact that pressure waves are actually a better description of sound waves than displacement waves. But you can imagine that sound is a displacement wave, right? You just have a bunch of little atoms moving left and right, and so that would be displacement. But you can see that the pressure waves are a little bit easier to describe because they're kind of obvious to see. So that's why we'll use pressure waves. But anyway, that's neither here nor there. Right, so that's what polarization is. Polarization is the direction that the thing would that the oscillators move in. So in the case of a string, the oscillators are moving up and down. In the case of air in a sound wave, the oscillators are moving left and right. In the case of light, it's not a physical thing oscillating. It's the electromagnetic field oscillating in a particular direction because it's a vector, and the vector goes up and then it goes down and then up and then down. And you'll see that in 9C. But the point is that the polarization is just a direction that is not the same as the direction that the wave travels in. It's an important point to make. All right, back to the regular lecture notes. Okay, so those are the properties of waves that I wanted to talk about. Now we can specialize even further. Let's talk about harmonic waves. So by the way, we were talking about just any old wave in any number of dimensions. Then we specialized to one-dimensional waves because they repeat their shape. Their shape doesn't change, they just move. Then we specialized to periodic waves. These are one-dimensional waves that repeat themselves forever and go on forever in every direction. We're going to specialize one more time to talk about harmonic waves. Also, I'm going to lose my voice at this rate. This is not good. So the simplest, we might want to try to figure out what is the simplest type of harmonic wave. And hopefully you guys all already have an idea of what that is. It's like sines and cosines, right? Yeah, you know what? They were out of Arizona green tea at Safeway yesterday when I went to the store. What can I do? Right, so the simplest type of periodic waves, I should say. Now, obviously simple is subjective, but you guys all know what I mean. Like this is going to have like the most basic functional form. And so this simplest type are called harmonic. And these are just sines and cosines. That's all they are. So a sine or a cosine would, or a harmonic wave is just a wave that's described by a sine or a cosine. And so you might just want to write f of x and t equals a sine of x, or sorry. Maybe you would write cosine of x plus 3 meters per second, because you have to put a speed there, and I'm plugging in just a speed. This might just be an example, plus or times t, right? You might just want to do that. And you'd be like, bam, there's a wave, we're done. But it's not quite that easy. This is actually not right. It doesn't make sense to write that, because cosine and sine must have unitless arguments. And I mean, the way to see this is that what type of thing do you typically plug in to cosines and sines? You plug in angles, right? And angles don't have units. Whereas this thing, x, or a speed times time, that has units of distance. You can't like take something with units. You can't like what is the cosine of like 6 meters? Or what's the cosine of 25 Fahrenheit? Like it doesn't make sense. It has to be unitless because cosine is a ratio. Ratios are unitless. So we need to fix this. And the way we do this is we just divide that argument by a distance. That'll make it unitless, right? We divide the argument, dividing by the appropriate units. And the appropriate units in this case, by the way, we are an SI only class. We use scientific, or we use it's something international. It's some French thing. We use SI units. We use the metric system in this class. We're not, anyway. The unit of distance in the SI system is meters. So we want to divide it by some number of meters. That'll make it so that it's unitless, and then we can just use that. But the question is, how many meters do we divide it by? Well, I mean, there's only really one choice. Like if we're describing a periodic wave, there's only one thing that describes the wave that has units of meters, and that would be wavelength. And we can see that relatively easily. If we take a snapshot, if we just divided it by 1 meter, well, then this distance would be 2 pi. But we want that distance to be 1 wavelength. And by the way, the reason that distance would be 2 pi is because this is like cosine of x, rather. Come on. The reason why it would be 2 pi is because sines and cosines repeat themselves every 2 pi, right? So if we want it to repeat itself every lambda meters wavelength, then we should divide by lambda and multiply by 2 pi. So basically what we're doing is we're going to shrink it by multiplying by 2 pi, we're shrinking the interval down to 1, and then by dividing by lambda, we're multiplying it out to be length lambda. So we multiply the argument by 2 pi over lambda. And that'll A, fix our units issue, and B, make sure that it repeats itself every lambda units. And so our next best guess is f of x and t equals cosine of 2 pi x over lambda plus 2 pi vt over lambda. And now this should check out. Yeah, that's sine of x, sorry. They're basically the same thing, don't worry about it. So this checks out. First, if we just choose some fixed time, this will repeat itself every lambda unit, or every lambda meters, right? Second, this is an argument that's unitless, so it's a ratio, so cosine makes sense. So this is good. Put a check mark by it. That's a good old wave. It has wave-like behavior because we could factor out 2 pi over lambda, and we could write it as x plus vt, right? So it behaves like a wave, and it's the argument is unitless, so we're good. Now, just as a quick note, V over lambda, which shows up here, that's just the frequency. I wish there was somebody named Kenneth in this class. I'd be making so many REM jokes. And this can also be written as 2 pi over t. That's not right. It can be written as 1 over t. The notes are wrong. I'll have to fix that. So, okay, that's great. This more or less describes what we want. But what if, and I'm actually going to make this cosine and I'm going to draw it properly, just so we have a good reference. What if we don't want the, what if we want to use cosine, but we don't want it to start at like the peak? What if we want it to start at like halfway up the peak or something? Well, that would still be a wave, but it wouldn't be a cosine of, you know, x plus vt. It wouldn't be a sine of x plus vt. We need to somehow shift it, and we can do that. So if the peak is not at x equals 0, t equals 0, then we can just add a phase constant. Phase constant is a technical word. It's a constant that changes the phase. Who would have thought, right? We add a phase constant, and we're going to use the Greek letter phi for that. It looks like a little O with a slash through it. You might also see somebody write it like this. These are the same letters. They're the same Greek letters, just one's cursive and one's not. And so now our wave equation, or a wave function, sorry, becomes cosine of 2 pi x over lambda plus 2 pi t over capital T plus phi. And now we're almost done. Because, by the way, so what this does is it just tells us where to start. And the reason is because if you plug in 0 for both x and t, then what you now get is you get cosine of phi, which is not necessarily equal to 1. That's, i.e., it's not necessarily at the peak. And it's only equal to 1 is, if phi is 2 pi or 4 pi, etc. So if phi is a multiple of twice pi, then yes, it will. This means nothing. But if phi was like pi over 19, then it would just be at some different place. It would start somewhere else. There's one last thing that we can do, one last modification that we can make, and that's, well, okay, what's the maximum value that this wave function takes on? Well, cosine is at its biggest, it's 1. At its smallest, it's -1. But what if we're describing a disturbance that's like 2 meters tall? Well, we need, like 1 doesn't have units, so we need to multiply it by something that has units that describe the disturbance. Right, if you multiply 1 by like 2 meters, then you'll get something that's 2 meters. And so we can actually adjust how big and what units this disturbance is in by multiplying by another number. So, so to change the disturbance, height, I'm putting height in quotes because it's not necessarily a physical height, multiply by a number. And by the way, all of these moves that we're doing, these still keep our wave function a wave function. You can test and plug it into the wave equation, and you'll still get that the wave equation holds. So now we can write our wave function as f of x and t equals a times cosine of 2 pi x over lambda plus 2 pi t over t plus phi. And here is our final form for our harmonic waves. This a, by the way, that is known as the amplitude. And by the way, we will talk about the power associated with harmonic waves today, actually. So you could, in theory, compute or create a harmonic wave whose power is over 9,000, if you so chose, right? And at that point, it would be in its final forms. I'm sorry, that was really bad. Anyway, at least somebody got it. Right, so that's the amplitude of our wave function. And so now, just as a quick aside, I'm using cosine here, but you guys might be like, well, cosine is like sine's little brother. Like there's sine, and then there's like the real sine, and then there's cosine, right? Like cosine is like the anyway. So why are we using cosine? Well, it doesn't actually matter, right? If you added pi over 2 or 3 pi over 2, that will shift the cosine so that it looks exactly like a sine. So you could use sine, you could use cosine. They are functionally identical. They just have different phase constants. So for the most part, I will use cosine just because I like that when you plug in 0, you get 1, but it really doesn't matter. You could use either or. Now, as a takeaway from this notion of harmonic waves, a harmonic wave is determined strictly by 4 numbers, right? Not 2, 4 numbers, right? Alpha, sorry, not alpha, A, the amplitude. That tells us how tall is the wave, how big is the disturbance. A sound wave, that amplitude might be a pressure. It'll tell you how much pressure is in that wave. Lambda tells us the wavelength. How far apart are peaks in space, right? For a sound wave that's really, really low, you might get like a meter. For sound waves that are really, really high, you might get like 2 millimeters. It varies depending on the wave. T tells us how long does it take for that wave to repeat itself. So like if you're standing on the shore of the ocean, or if you're standing on the beach, what's the time between wave troughs hitting the beach? Well, that would be the period. That would be T. And then finally, phi, that just tells us where did the wave start? Like if you snapped on the universe at t equals 0, what would the wave's like position be at? Like would it be at its peak? Would it be at its trough? Would it be somewhere in the middle? That's what phi tells us. It tells us where the wave is along its cycle. And so every wave can be described this way. And in fact, you can kind of just plot it. So it's kind of hard to plot t at the same time, but we can plot f of x and say 0. So if our wave looks something like this is x, then this distance here, that distance would be a. This distance here, the distance from 0 to the peak, that would be phi. That's the phase constant, right? It tells you how far away you are from peak. This distance, the distance between peaks. Now, by the way, it's not quite phi. That'd be like phi over lambda or something like that. This is, I'm going to say it's roughly phi. It tells us where the peak is. This distance here is lambda. And so you can see that knowing these 4 numbers tell you how to like graph the wave function, which is super useful. Like just, it's handy. It's handy dandy. Also, we're making pretty good time, so I'm happy. Actually, are we? Just got through page 7. Right, so there's 2 more links that are in the lecture notes that use this notion of harmonic wave. Oh, somebody has to mute. Okay, uses this notion of harmonic waves to like test your understanding. So go take a look at those. Again, they'll be posted in the lecture notes afterwards. There will be links. Okay, so there's one thing that I'm not going to spend time on in lecture today, which is in the LibreText and that you should look at, you will be responsible for. I'm not going to spend time on it because it's a really messy derivation and it requires good diagrams that I can't draw by hand. But this is the notion of wave speed. So I'm just going to tell you what the results are, and I'll tell you that the derivation is in chapter 1.2 in the LibreText. So what is done in the LibreText and what I would have done, but I don't think I'll have time for it, and the diagrams are really messy, is I would use Newton's laws basically, and standard calculus tricks to find the wave speed on a string, or we want to find the wave speed of a transverse wave on a string. So like this is the simple picture where you have a string that's like pulled taut. It's like attached at the other end of the wall. You go like this. How fast does the wave travel down? You can just figure that out from like Newton's laws. The end result is that the wave speed is equal to the square root of the tension force on the string. So the string has to be under tension for this to work. Otherwise it'll just kind of flop. Divided by mu. So here, F is the tension on the string, and mu is the linear mass density of the string. Now you guys all took 9A, so linear mass density shouldn't be unfamiliar. We used lambda for linear mass density in 9A, but we don't want to use that because it's wavelength here. So it's linear mass density. It's what is the mass for say 1 meter of this length. So this already should tell you something interesting. For example, on a guitar, which would be an example of a transverse wave on a string, the more tension the guitar string is under, i.e. the more that you turn your knobs, nuts, there's a word there, like the string tuning thing. I played guitar for a long time, but I haven't played in a while, and I don't remember what it's called. Key, thank you. Sure. The more you turn it, the higher your tension goes, and you can feel that it takes more and more effort to turn it. But as you turn it, the tension increases, and so the wave speed increases. Now, we will see how the wave speed is related to the, like later, we'll see how the wave speed is related to the frequency that is played by that string when we talk about standing waves. But you can see that that increasing the tension is going to change something about the wave. Similarly, if you use lighter or smaller gauge strings, like strings that are smaller, their linear mass density will go down. And so that would have the same effect as using more tension. So this is why, that is a mu. This is why you could either tune your guitar so that there's a lot of tension on the heavy strings, or you can just replace it with a lighter string and you can get the same effect. Anyway, so that's a result that we're going to use. So keep that in mind. It's not super hard to derive, but the diagrams do require a lot of precision that I just don't have by hand. So just as a key point to make, these wave attributes that I mentioned, these 4 wave attributes, we can characterize which of them are properties of the medium that's like that the wave is traveling through, and which of them are properties of the thing that caused the wave. So let's just break that down really quick. By the way, a derivation for the wave speed and for other types of waves will be different. This is just a simple example of a wave on a string. So the wave speed, as we see in the example above, this is a property of the medium. It depends on the medium through which the wave travels. In this case, for a wave on a string, it depends on the tension on the string and the density of the string. It doesn't depend on like how hard you pluck it. That doesn't affect the wave speed. It's just the string itself. The amplitude, on the other hand, that is related to the, I'm going to put this in quotes because it's not actually power. It's related to the power of the driver. Now, the driver would be like, how hard do you pluck the string? Or like if you attach like a pneumatic piston that goes up and down, that would be like, how high is the pneumatic piston going? Is it going up and down a lot or up and down just a little bit? That will affect the height of the disturbance. The amplitude. The period of the wave, well, that is the rate at which the driver cycles. So if the driver, the thing that's causing the oscillation, goes up and down slowly, the period will be as slow as the driver goes. But if it goes up and down really fast, the waves will go really fast. Like they'll oscillate really quickly. And then finally, the wavelength. Well, we know the wavelength is related to the speed and the period. So in this case, the wavelength on the string or in whatever medium, this depends on both. It depends on the medium and the driver. So like, for example, if you wanted to increase the, if you like, typically we can't control the medium, but we can control the driver, the thing that's causing the waves. So like, how would you change the amplitude if you're a guitar player? Well, you hit the guitar string harder. That would change the amplitude, right? Because you are the driver, like your pick or your fingers are the driver. But you can't really change the wave speed in the guitar string unless you change the guitar string itself by retuning it. Right, so we have one more segment to cover. This is section 1.3 in the LibreText to cover today. And that's wave energy and power, or wave energy and power transmission. So we're going to continue talking about, and by the way, the reason why we're talking about this is because clearly waves transmit energy, right? And the reason I say clearly is because, like, let me think of an example. Light's a wave. Light comes from or sunlight anyway, sunlight comes from the sun. All of the energy from sunlight starts off at the sun, and then somehow it makes its way to the earth, and then we can harvest it in the form of like electricity with solar panels, or we can heat up water with it, or whatever. So clearly energy goes from place A to place B, and it's carried by a wave. The question is how, and how much? So what we can do is we can start with just one-dimensional waves and understand those, and then we'll use that to understand 2- and 3-dimensional waves, which are a little bit more realistic, more useful. So we're going to continue with a one-dimensional wave, and we're going to continue the simplest example. We're going to consider a wave traveling down a string. So, well, how do we figure out how much energy is in an oscillation? Well, it's kind of hard. So we're going to make an approximation. We're going to treat each point in the medium. By the way, I don't think I defined this, but a medium is the material through which a wave travels. So like air is the medium for sound. Water is the medium for ocean waves. The string is the medium through which a transverse wave travels through it. So we're going to treat each point in the medium like a simple oscillator, like a mass attached to a spring. So the picture is, and by the way, this is a reasonable thing to do because so here's our base level string, but like each mass or each part of the string is oscillating up and down in time, right? And so if we want to figure out the energy, all we have to do is find out the energy of each of these little springs and then add them up. And so this distance here, by the way, would be the amplitude. Now, why can we do this? Well, it turns out that it's a reasonable thing to do. There is maybe the spring isn't actually in the vertical direction, but as far as we're concerned, the pieces of the string aren't moving back and forth. They're only moving up and down. And further than that, there is a restoring force on each of these strings. As they go higher, they're pulled on harder by their neighbors. So their neighbors are going to pull them down. And as they go lower, their neighbors will pull them up. So there is a restoring force that behaves a lot like just a spring would. So this is a totally reasonable approximation. So the question is how does this transmit energy and how much energy does it have? So let's answer the second question first to figure out how much energy this wave might have. So we already know how to find the energy of a single oscillator. The energy of a single oscillator is just the kinetic energy plus the potential energy. It's 1/2 mv squared plus 1/2, say, ky squared. Maybe y is the vertical direction. And 0, when it's at 0 height, it's level. And k is whatever the spring constant is. Now, that spring's not really there, so we'll have to get rid of it at the end of the day. Now, because this system, we're assuming that there's no friction or anything. This is an ideal system that we're trying to imagine anyway. In this case, energy is conserved. So we could evaluate it. We could find the total energy by finding the energy at any point in time. And we don't really want to worry about how fast the string is moving up and down. And we already know how high the maximum height is that this spring goes. Yeah, this is total energy. I'm just not using etot because we're going to use it for something else. So the total energy can be found by evaluating at the peak. And so at the peak, the speed is 0, v equals 0, and the height is just the amplitude. Yeah, 1/2 ky squared is potential energy. Yeah, that's from 9A. Hopefully you guys remember that. So then the total energy of the single oscillator is just 1/2 ka squared, which is great. That is just the energy of a single spring. And that's partially, at least, in terms of our wave, in terms of the variables that we use to describe our wave. Now, like I said, strings aren't actually made of springs, right? They're made of molecules and fibers and threads and all that business. So how do we relate k, this constant that is some made up thing that was just used as a model, to the actual wave properties? Well, for a spring, we actually can relate the rate at which we can relate the spring constant to the rate at which the spring oscillates up and down. In particular, 2 pi f, which is also known as omega, the angular frequency. This takes some work, and you may not have seen this in 9a, but it turns out that this is related to the spring constant divided by the mass of the thing attached to the spring. And so, in particular, the spring constant k is just equal to the mass times 2 pi f squared, the frequency. So the frequency is a thing that that is part of our description of a wave, right? The frequency tells us how quickly a particle moves up and down, and that's exactly what the frequency means in this context too. So for a string wave, oh no, did I not update my notes? Oh yeah, for a string wave, just for like a little chunk of string, the total energy, or the energy in that string, in that chunk of string, is 1/2 times m times 2 pi f squared times a squared. Okay, great. That is the energy in just a little chunk. But that's not the whole story, right? Because there's a whole bunch of these. And what we don't know what the mass is of a little chunk, but we can use the tricks that we used in 9a to figure out how this small amount of energy relates to the total energy in, say, a single wavelength. Now we know that the wave propagates. It propagates down the string or across the string. So we might ask, how much energy is in a single wavelength? Right? So we're going to try to figure out how quickly this wave transmits energy. And one way that we're going to do that is we're going to say, okay, one wavelength has this much energy. We know how fast a wavelength moves. It goes from here to here in a certain amount of time. So we can use that to figure out the rate at which that energy is transferred from here to here. And that would be a good way to figure out power, or rate at which energy is transferred. So we want to figure out how much energy is in a single wavelength, so we can do that. Remember, a wavelength has length lambda. So we're going to use the trick, and by the way, we're just going to assume that this wave is just like a single pulse of a wavelength. So like the picture is actually, no, I'll draw this picture later. So what we're going to do is we're going to treat each particle in the wave as if it were infinitesimal. Then we can figure out the wave in terms of the mass in terms of the length and the density. So the mass would be dm, and the length is dx. Let's say like a very small length of string has mass dm, and it's moving up and down. So then the mass density is related to the ratio of the mass and the length. In particular, you guys remember this from 9a, the amount of mass that the thing has, that little piece of string has, is equal to mu, which is the linear mass density, times the length. So the energy in our little itty bitty type piece of string that's moving up and down is 1/2 times 2 pi f squared times a squared times mu dx. This is the same mu as before, by the way. And so the total energy, thus, that's a fancy word, the total energy in one wavelength is just found by adding up all of these little energies. So it's an integral, because we're adding up a bunch of infinitesimally small things, integrating from 0 to lambda of 1/2 2 pi f squared a squared mu dx. And so this is just a really easy integral to do. It's just a constant times dx. This is just equal to 1/2 times 2 pi f squared a squared mu lambda. This is just the length, or that is the total energy contained in a wave, or contained in a single wavelength of a wave on a string. So the rate at which, so what is the rate at which this energy is delivered? Well, we would describe that with power. Power is energy over time, as I already mentioned. And so if you have, say, one end, let's say you have two things that are connected to each other. That's that two wavelengths apart, right? They're connected by a string. If you wiggle one string, that it will take that string a certain amount of, or that wave a certain amount of time to get to the other side. And the amount of time that it takes divided by the total energy divided by the amount of time that it takes is precisely the rate at which that energy was transferred. Because you could do that again and again and again, and it would transfer that much energy in that amount of time. For this wave, it takes t, which is the period, seconds to deliver one wavelength worth of energy. And so the power in the wave would just be the total. Oh, this should be E total, sorry. Should be the total, or actually, let me not even call it E total. Let me call it E lambda, the energy of a single wavelength, divided by the period. So this is 1/2 mu 2 pi f squared a squared lambda over t. Now, but lambda over t is just a number that we already know. That's v. It's the wave speed, 1/2 mu times 2 pi f squared a squared times v. And so this is the power that a string or a wave on a string transmits. This is the rate at which energy is transmitted from one end of the string to the other end of the string. And assuming there's no friction, this is a 100% efficient process. It takes all of the energy from one end, puts it on the other end. And the rate at which it transfers that depends on the speed. Of course it does, because the wave has to move from one end to the other. It depends on how high the oscillation is. If you're oscillating a lot, then you're transferring a lot of energy in a certain amount of time. And if the string is heavier, it's going to take more effort on your end to get it moving, to get it to oscillate a lot. So of course it will depend on the mass of the string. It'll also depend on how fast you wiggle it. If you wiggle it fast, it's going to take a lot more work than wiggling it slowly. All of these things add up to make sense. Now, if you recall from before, this is where I just gave you the answer. The speed on a string is given by the tension in the string divided by mu. And so in particular for this string, the power in the wave can be broken down even further. It's 1/2 times the square root of mu times the tension force. It's the power delivered by the wave. P stands for power. Times 2 pi f squared times a squared. And so the important point is that this, the thing that determines the power in the wave depends almost entirely, or it depends on both the medium and the amplitude, but you can control the power by just changing the driver, i.e. you can change the frequency, you can change the amplitude, no problem, and that will change the power delivered. An important point that shows up frequently is that the power delivered by a wave is proportional to a squared, proportional to the square of the amplitude. That's super important because it shows up, it turns out that this is true for all 1D waves. Any type of one-dimensional wave transmits power in a way that's proportional to its amplitude squared. Okay, so now we're getting to the end-ish. Oh, we're actually making good time. What about two-dimensional or three-dimensional waves? Well, we can ask what's going on with the power transmission there, but it's a little bit less clear. Like, what's wavelength for a two-dimensional wave? Well, that's probably fine because it's the distance between peaks and troughs. But the peaks and troughs are getting shorter, right? Like, think of the ripple on the pond. So, like, how do you actually measure that distance? Because it doesn't go back to the same height ever, it goes down. Frequency, again, you could probably figure that out by just asking, well, if you look at a single place, how long does it take to go up and down? That's probably reasonable. You can probably get a frequency. And what about amplitude? Amplitude, well, amplitude tells you the height of the wave, but the height is changing. So maybe it's just the amplitude at a certain place, and the amplitude changes with position. things get tricky, as you can see, right? But we can still do something. So assuming no energy is lost to like friction or dissipative effects, 2D and 3D waves conserve energy, just like the one-dimensional wave. So we can figure out how much energy is transmitted. Now maybe we can't figure it out explicitly, but we can at least do something. So I want to make sure that we, okay, yeah, I want to make sure I wasn't missing anything. So the fact that they conserve energy should mean that the amount of energy contained in one ripple should be the same amount of energy contained in any other ripple, because that ripple isn't losing energy and it's just getting bigger and bigger. So even though the amplitude is going down, the energy that that wave carries should be the same. It shouldn't change with time because the energy is not lost anywhere, right? Energy is conserved. So what that means is that the energy transmission, or the power transmission, the rate of power transmission, should be constant. Shouldn't change with time, it shouldn't change with position. And yet, as I said, amplitude decreases with distance. And that's just because it's spreading out. And so it cannot be the case, unlike in the one-dimensional case, where the power is proportional to the amplitude squared. An example of a 3D wave would be sound. Travels all around 3 dimensions, right? But it's a pressure wave, or it's a longitudinal wave, so it's a little bit harder to visualize. So, I mean, a lot of what happens in 2-dimensional waves also happens in 3-dimensional waves. So for a lot of our purposes, we can just try to use our intuition for 2-dimensional waves, which are at least like the surface of a drum, are at least easier to visualize. Right, so amplitude decreases with distance, so it can't be the case that the power is proportional to amplitude. Or sorry, to amplitude squared, because the power has to be constant anywhere at any time. And if the amplitude is changing at different places, then if the power is proportional to the amplitude squared, then the amplitude would be changing. So that is, power is not proportional to amplitude squared for 2D or 3D waves. So how do we account for this fact that the power, like the amplitude's decreasing, but somehow the power stays the same? Because obviously the height of the wave affects the energy in the wave, so it has to be involved somehow. Well, consider this. If we use the same sort of analysis for like the ripple on a, no, the speed doesn't get faster. No, but that's a good guess actually. If we use the same sort of analysis for like the ripple on a pond, right? And we treat each molecule of water as its own little oscillator, because it's going to go up and down as the wave passes by. Well, yes, the amplitude decreases as you get further out, but what doesn't decrease? In fact, what increases? Well, as the wave gets more and more spread out, there's more particles in any given like ring of the wave. So even though the amplitude goes down, the number of particles goes up. The size of the wavefront increases precisely. So even though, oh boy, even though A decreases with R, the number of oscillators increases. And so that will account for our loss of energy. That will precisely do what we want it to do. In fact, think about a 2D wave. So for a 2D wave, if the radius of the wavefront, which is just like a single ripple, right? If the radius of that wavefront, if it starts off at like 1 meter in radius and then it doubles to 2 meter in radius, well, how many more particles are in the larger wavefront? Well, the radius doubled, so that means that the circumference doubled. And so if the circumference doubled, then there should be twice as many particles, right? So the energy in that wavefront stays the same, or in that wavelength rather, but the number of particles doubles. So that means, but also we know that the energy per oscillator, like the energy in a single oscillator, like what we did in the one-dimensional case, is still proportional to the amplitude squared. So the total energy in the wavefront, or E lambda, would be equal to, when it's 1 meter in radius, it would be equal to the number of oscillators in that wavefront times the energy of each oscillator in that wavefront, which would be proportional to amplitude squared. But this should be equal to the number of particles in the 2 meter wide wavefront times the energy of each of those oscillators in that 2 meter wide wavefront. We also know that the number of particles, this is for 2D, the number of oscillators, the number of particles, yes, CB, actually, we're going to get to that. Good, that's a good observation. The number of particles doubles, or it increases linearly with radius. So n is proportional to r being the distance from the center. And the energy is still, the energy per oscillator is still proportional to amplitude squared, right? That's just because it's still just a spring. And so what this implies, it implies that R1 times the amplitude at position 1, A1 squared, should be equal to R2 times A2 squared. And what does this get us? Well, this gets us a proportionality, because that means that this is just a constant, right? It's just basically proportional, that constant is related to the total energy. So this tells us that the amplitude of a 2D wave is proportional, roughly proportional, at least at large distances, to 1 over the square root of the distance. And so this is how the amplitude changes with distance. As you get further away, the amplitude is going to go down like 1 over square root r. And you can do the same thing for 3-dimensional waves too. For 3-dimensional waves, the amplitude will go down as 1 over r, not 1 over square root r. And so what's happening here is the amplitude is decreasing to account for the energies being spread out over a large area. So like take an amplitude, if you draw it out to one circumference, that amplitude is going to decrease as it gets spread out. If you spread it out even more, it'll decrease even more, but it's just that energy isn't going anywhere, it's just spreading out. And this leads us to another notion. This is the notion of intensity. So intensity is a way of describing the amount of energy that's spread out, or the rate, the amount of, or how much the power is spread out. So intensity, let me give a more specific phrasing. This is the density of power flux. So power is energy going from place A to place B in a certain amount of time. So power flux is the rate at which energy crosses some boundary. So the density just tells us, well, okay, the density of the power flux just tells us how is that power transmission like spread out. So of course, over the whole wavefront, it's not changing. But as the wavefront gets bigger, well, each little chunk of that wavefront carries less of that power. Its power density is less. And so we can relate that to the distance and the power. So for 2D waves, the intensity I, as a function of r, because the intensity does change with distance, this would be the power of the source, how much power is delivered by the thing causing the wave, divided by the circumference, because all of that power is spread out over the circumference of a circle. And in 3D, this is for 3D waves, so like clapping, the intensity goes as the power of the source, because it's still the same amount of power, but it's just smeared out over the surface area of a sphere, which is 4 pi r squared. So in 2D it doubles, and in 3D it squares. Yeah, I already answered that. And so this is how the energy spreads out. And in fact, in three dimensions, we give this relationship a fancy name. We call this the inverse square law. Which just says that R1 times I of R1, sorry, R1 squared times I of R1 is equal to R2 squared times I of R2. By the way, this is the same inverse square law that you see in gravity. Gravity happens to be propagating by waves. I wonder if they're related. Of course they're related. Now, just as a recap, for two-dimensional waves, 1 over r is proportional to a squared, right? Because a is proportional to 1 over r square root of r. And for 3D waves, we could have done the same thing, and we would have found that 1 over r squared is proportional to a squared. So in all cases, including one-dimensional waves, the intensity is proportional to the amplitude squared. That's true regardless. But the intensity goes down as you get further away. So, wow, that is the first time that's ever happened. Here's what I just wrote down. Here's my notes page. See this? This is nothing left. We finished on time, exactly at 11:40. I'm very proud of us. I'm proud of me, I guess, because I timed it perfectly. That's very surprising, though. Anyway, so that's the end of today's lecture. I'm going to post these lecture notes. I'm going to post these lecture notes. I will link to the recording at, oh boy. Okay, good, I was recording. I know it was a lot of information. Summer classes are fast. You're gonna have to, for 1D, it's just that the amplitude is constant. It doesn't change with position. Anyway, right, so summer classes are fast. This is like 9B is probably the most straightforward mathematically speaking, but there's a lot of information, a lot of concepts. 9B is probably the hardest conceptually. So you're gonna have to spend a lot of time thinking about this. Work examples so you can get the intuition being built. I is intensity. It is the power density, power flux density. So you're gonna have to spend some time. Remember, the Discord is your friend. You should be spending plenty of time in there. Well, considering that there's, oh, let me stop recording because I don't need to be recording for these.